Okay, let's get started. Before we jump back to lecture, just wanted to talk a little bit about the assignments. So you're working on assignments 7 and 8 now. I know that some of you are still struggling with 6 and a few of you are still struggling with 5. So I wanted to just point out a few aspects of the ragdoll demo that might help for some of you that are still struggling with 5 and 6. Okay. I think for some of you, you might have actually had some errors with how you were actually placing the body parts, which then makes it very difficult to figure out how to add the joints and make sure that the joints are in the right place and the joint normals and so on. So if you go back and have a look at the ragdoll demo, you'll see that there's 2 data structures that are used to create each body part making up the ragdoll. There's the offset and the transform. So let's draw our 3-dimensional axes here. So X is our horizontal axis, Z points into and out of the screen, and Y is our vertical axis. So if you go and have a look in Ragdoll, you'll find that this offset is set up at the top before all the other body parts are defined, and the offset is past this vector called position offset, which, as the name implies, that position offset, which I think for the ragdoll is at 0, it's at some height, I don't remember what it is, x0, y, for example, 1, z equals to 0. This is the offset. And then the transform is a data structure that is going to say, how are the body parts attached, how are the body parts positioned relative to the offset? So the value that's stored in transform, that number there is a position, but it's a position that's relative to the offset. So for example, if our offset is 0, 1, 0, and we want to place, for example, the left arm, we can place the left arm with a transform t of 1, 0, 0, which means place the arm 1 unit to the left of the position offset. Okay, so the offset is given in absolute coordinates. So absolute coordinates is what exactly is that point in 3-dimensional space. And the transform is given in relative coordinates, right? Coordinates that are not relative to the absolute frame, they're relative to something else, which in this case is our offset. So you'll notice that in here we have offset times transform. So that's Bullet doing some work for you of just figuring out where the actual position of the arm should be. We won't get into the 3D geometry for doing this, but I think that should be clear. So why are they using this offset for the ragdoll? Why not just define all of the positions of the ragdoll in absolute coordinates?
Then if you make more than one ragdoll, you can have that. You can say where you want to make that ragdoll, and not have to rethink of where all the coordinates have to be.
Exactly. So if you go back and play with the ragdoll demo, you can create an arbitrary number of ragdolls, and it's easy if you do it in this way because, as Tyler was just mentioning, we could define a new offset which is at 1 unit to the right, 1 unit up, and 0 units into or out of the screen. And now we can just call all the same code again. The only difference now is that offset is going to be different. So it's going to create an entirely new ragdoll at this new position. For the quadruped, at least for the first 10 assignments, you're only going to have 1 quadruped. So you can make your life easier if you haven't done this already by setting the offset to be at 0, 0, 0. Or you can do away with the offset altogether. And here, instead of having something like offset times transform, you can just have just one data structure, which is the transform itself. Doesn't really matter. Okay, so if you blindly copied over some of the code from Ragdoll and you still had an offset which is not sitting at the origin, then you might be confused. If you think you're trying to add a part of the robot at 1, 0, 0, it is not going to appear at position 1, 0, 0. Yeah? Okay, hopefully that clarifies things a little bit. Okay, that might help you, some of you that are still working on assignment 5. Assignment 6. If you're still working on assignment 6, I added a little note here in the subreddit. You can actually see the positions of the joint and the joint normals. If you hit Shift L and or Shift C, you'll actually see a little coordinate frame that's sitting exactly where the initial position of the joint. And then as the robot starts to move, that little graphic will move as the robot moves. I forgot about that little piece. Somebody reminded me of that. I apologize. Hopefully that will also help clarify things if you're still struggling with joint positions and normals. Okay, that's assignment 6. You're now working on 7 and 8 where you're adding motors and sensors to the robot. Any questions about 7 and 8? No, we're all good? Okay, so let's jump back to lecture. There seem to be a lot of coincidences happening in this course this semester. So when we were talking about neural networks and backpropagation, unfortunately one of the founding fathers of backpropagation, Marvin Minsky, passed away. Then we talked about embodied and disembodied approaches to AI, and at that time there was an AI program that was released that won at Go. We just finished talking about we were talking about bipedal locomotion. On Tuesday, I got back to my office, and about an hour after I got back to my office, Boston Dynamics released their latest video of Atlas, their biped robot. People see this video in the last couple days. Quite impressive. And a little unnerving, absolutely. You'll notice it's still got a backpack there somewhere. What's in the backpack? The battery. Right? Very high-powered robot. Not much passive dynamics going on here. In this case, I'm not sure. I think it's pneumatic. Probably. Sounds like servo. Combining legged locomotion with object manipulation, this is extremely difficult in robotics. Roboticists seem to have a sadistic streak here. I don't know why. Another extremely challenging issue for legged robotics, getting back up. Okay, so some very impressive recent advances in legged locomotion, right? Okay, we were looking last time at a specific aspect of legged locomotion, was this issue of passive dynamic locomotion. One of the reasons to be a biped is if you get the gait right, you can be extremely energy efficient. So just to remind ourselves, we just saw Atlas and Asimo, very sophisticated walking, but not very energy efficient. We saw the other extreme end of the scale last time, the passive dynamic walker that has no motors or sensors or neural control whatsoever. And we worked our way last time through an evolutionary robotics experiment where the idea was to try and automate this process of designing a robot that can exhibit or that can evolve, first of all, passive dynamic walking. Once it does, can we then evolve that robot further to add hybrid dynamic walking? We saw last time, for the first time, we saw an experiment where now we're broadening evolution's reach. So now the genome contains morphological parameters that dictate the physical construction of the robot and neurological parameters of the robot, right? Parameters that describe the neural controller of the robot. We worked out last time that there were 22 morphological parameters that were under evolutionary control. In addition to those morphological parameters, some or all of the synaptic weights in the neural network can be evolved. And we saw that this evolutionary process was actually a multi-stage process where we're going to do passive dynamic walking first and then hybrid dynamic walking. We introduced this idea of a central pattern generator, which is like the conductor of the orchestra. It gives out a pulse every once in a while. It sends a pulse into the neural network, the pulse controlling the neural network that controls the left leg. Then, in some cases, it sends a pulse to the right leg, and the right leg has exactly the same neural network, right? So there are two identical copies of the neural network in the robot. Okay, we looked at the fitness function last time, which tries to maximize D, or displacement or movement, and it also tries to minimize all these different kinds of silly walks, so don't exaggerate your movement as you're displacing from the top of the declined plane to the bottom of the declined plane. So just as a reminder, we're going to see this form quite a bit in the course. When you see something like this, you usually know that t is minimized, or evolution is punishing large values of t. If a variable is sitting by itself, we're usually trying to maximize that value. Right? Okay, so I think we got about this far last time. So here we're using, in this experiment, they use this idea of shaping or scaffolding. It's an idea we mentioned earlier in the course, which is basically start evolution and make things easy on the robot. So let evolution get started, and once you get the rudiments of the behavior that you want, then you can, in essence, kind of remove the scaffolding or remove the training wheels from the bicycle. And now that the task becomes more difficult, evolution continues and enhances the rudimentary form of this behavior that you got in step one. So here, the rudimentary behavior we're after is passive dynamic walking. That is it's not very robust, right? It only works on a declined plane with this angle. Once we get passive dynamic walking, we're going to pause evolution, make a few changes, then turn evolution back on, and now we're going to change the fitness function a little bit to select for hybrid dynamic walking. And then the third stage, they're going to then fold in the sensors so that, like Atlas you just saw, it can react when there's a change to the environment. Okay, so how does passive dynamic walking work? Well, in this case, the genome contained each genome contained 22 body parameters, which dictated how to build the robot, and just the synaptic weights that connect the CPG at the top here to the hidden neurons, and the synapses that then connect the hidden neurons onto the motor neurons. Right? So the sensors aren't attached here. So you can see in step one here, I've tried to break things up into evolution and evaluation. So remember, we always have a population of genomes. Each genome contains 22 body parameters and however many synaptic weights that is. We take each one of those genomes, we physically construct the robot, we take the synaptic weights, and we label the neural network, put the robot at the top of the declined plane, and then evaluate that robot, right? So during the evaluation of each genome in the population, we put the robot at the top of the declined plane, we allow the CPG to send in just one pulse, so there's a little bit of actuation right at the beginning, at the first time step. The CPG goes silent, there's no more force that's applied into the neural network. And after the pulse, it's turned off, and we just watch how far the robot walks down the decline plane, and we assign fitness according to our fitness function. Rinse and repeat. We do that for every genome in the population. We throw away the controllers that are the robots that have low fitness, make randomly modified copies of the ones that remain, evaluate the new robots, and repeat for a number of generations until we have a robot that successfully walks passively to the bottom of the declined plane, right? However long that takes. Once that happens, that's the end of step one, and now we're going to take those robots that are capable, those one or more robots that are capable of passive dynamic walking, and now we're going to try and add in hybrid dynamic walking. Okay, that was a very quick summary of everything we went over last time. Okay, I think actually we got to hybrid walking last time, right? So now we're going to continue. Evolution is more or less the same. We haven't made any change to the genome. We're going to continue to evolve these 22 body parameters and the sets of synaptic weights that connect the CPGs to the motors. We're going to add in an additional fitness function here, which is 1 over 1 plus v. So you know immediately we're trying to minimize v. And so we're trying to minimize the difference between how the robot moves, or more specifically, the velocities of the parts that make up the robot, and how it moves when we put it not on the declined plane, but maybe on a shallower plane or eventually on flat ground altogether. So we're trying to challenge the robot to exhibit passive dynamic walking when we put it on the declined plane, and hybrid dynamic walking when we put it on a shallow plane or flat ground, and those two behaviors should be as similar to one another as possible. The velocity profiles over time of the body parts should match up. We're trying to minimize that difference. So far, so good? Okay, so now in step 2, we're evaluating every robot twice, right? We put it at the top of the declined plane, see how it does going down the plane, and then at the beginning of step 2, we decrease the angle of the declined plane by a very little bit, right? So there's not much of a difference, and evaluate it again, and do that for every genome in the population. At the second generation, in step 2, we do the same thing again. Every robot is evaluated twice on the declined plane and now on an even shallower plane. So over generations, over evolutionary time in step 2, the declined plane is slowly decreasing until eventually at the end of phase 2, in every generation, we're evaluating the robot on the declined plane and flat ground. Right? So these gradual changes that are occurring over evolutionary time. Okay. During the evaluation of any one controller, as we mentioned last time, what should be the frequency of the CPG? Well, we let the robot dictate what its frequency should be, right? The CPG gives one pulse at the beginning of the evaluation period. The robot starts to fall forward, and the moment the heel strikes the ground, we measure how many time steps it takes for that to happen. That time span becomes the beat at which the CPG beats, right? It may be different for different robots. Remember that we're evolving the body parameters. So in the population, we might have taller or shorter robots. What can you tell me about the CPG frequency for a taller robot compared to a shorter robot? What's that? Slower for which one? For the taller robot, right? The taller robot, it's going to take longer for its heel to strike the ground. It's going to have a lower frequency, right? We actually saw that, I think, when we looked at some figures from Alexander's book on locomotion. You can see that for humans. Tall humans tend to take longer to take one step than shorter humans, right? Same thing here. Okay, so far so good? All right, so at the end of phase 2, now they have a population of robots that can achieve passive dynamic walking on the declined plane, and if you put the robot on the flat and the CPG beats at whatever frequency that robot wants, it will exhibit hybrid dynamic walking, where if we go back to the neural network for a moment, the moment the CPG pulses for that leg, there's a pulse of values that arrive at the hidden neurons and then arrive at the legs. and desired velocities are applied to the joints, or actually applied to the springs, right? The robot jerks, it tries to move, and then what happens the next time step in the simulation? So at one time step, we input this CPG pulse. The motor neurons send desired velocities to the springs, which causes the springs to actively expand or contract. What happens in the next time step? They go limp, right? So you go back to having a passive or ragdoll robot, right? And it's limp until the next heel comes in contact with the ground. The CPG beats again, now on the right leg. The right leg does something, then it goes limp again. So this is the hybrid dynamic walking, right? It supplies a little bit of a force and then goes limp again. Okay. After this, now they go into a third stage. So this is still one long evolutionary run, but now they're going to fold in the sensors. Because if you don't have sensor input, this robot may be able to walk, but if there's any perturbation to the ground, or somebody enters the screen with a hockey stick and pushes, right, you're in trouble. So you need to have sensors to be able to detect any disturbance to the way you're moving and evolve a way to recover. So in this case here, again, I've broken things up into evolution and evaluation. Now they make a slight change to the neural network, which is they reconnect the sensors to the hidden neurons by supplying all these synaptic weights with values that are very close to 0. Why not just apply random values to those new synapses and let them evolve through phase 3? Why start by setting those values very close to 0?
So it'll minimize effort?
It'll minimize,
Energy expenditure?
not energy expenditure, right? That's still sort of, well, actually that might be, right? The more the sensors are connected to the neural network, the more non-zero values you're going to get arriving at the motor neuron. So that's true. The more sensory input, probably the less passive dynamic walking you're going to get.
It won't break what we've already done because we haven't had input from them, so they've already been technically 0.
Exactly, right? So up until this point, these have all been 0 already. If you suddenly make them large magnitude values, you're going to break these evolved connections here, right? In essence, you're kind of taking the blindfold off the robot and suddenly it's getting a huge amount of sensation that it's never got before and it's reacting to this unfamiliar input and you're very likely to break the gate that you've already evolved. So by starting with synaptic weights that are very close to 0, it's like having a blindfold and you're very gradually allowing the robot to see the world around it or feel the world around it. Remember, this is all the sensation that the robot has access to. And it's slowly evolving over evolutionary time in phase 3 how to exploit that sensory information to deal with any disturbances in its environment. Okay. As they do that, they just continue evolution like before with the same fitness function, still including 1 over 1 plus v. They're still evolving the body parameters. They're now evolving all the neural network parameter weights or the synaptic weights. So now everything is under evolutionary control and they evaluate like before. Put the robot once on the declined plane, once on the flat, and continue. Okay. This is a nice plot to try and get a feel for what this robot is doing. Again, unfortunately, they didn't capture any videos from their experiments. So here is one evolved robot walking. So we've got 250 time steps. Is this passive dynamic walking or hybrid dynamic walking? And how do you know from this image?
It's the hybrid, the CPG is spiking every time.
Exactly. So you can see that for this robot, it has a particular morphology and a particular way of moving that causes the CPG to beat every, whatever that is, 37 time steps and so. What happens when a leg receives a beat from the CPG? In this case, for this robot. Let's look at the hip to start with. So hip, the pink line here is basically recording the motor output that's arriving at just one of the hips. So they're not showing the other leg because the other leg does exactly the same thing, but it just does it in antiphase. So we're only looking at one of the two hip joints. Remember that the motor output is desired velocity, right? The motor is saying, or the motor actually applies rotational force, or sorry, not rotational force, it's pulling or pushing the spring to try and get the joint to rotate at a desired velocity. So this is velocity control, which is different from what you're doing with your quadruped, which is position control. In your case, you're saying, I want the angle of the joint to reach some desired angle and then hold it there. This is velocity control. So what's happening to the hip? Try and mentally simulate how this robot is moving, given this figure. What happens when the hip receives this CPG pulse? It swings forward, right? So this rapid increase here is the hip swinging forward. It swings forward pretty rapidly, right? The slope of increase here is quite steep. Then what happens?
Kicks. The knee kicks.
The knee kicks a little bit. So if you look at the knee, that's following as well. So the knee is rotating backwards, right? So it can't hyperextend its knee. So in this case, a non-zero velocity for the knee is telling it to rotate the knee backwards a little bit. Why does the robot rotate its knee backward at this point in the step?
Keep the lower half of the leg perpendicular to the ground.
To keep it perpendicular to the ground. It probably does, but that's not why it's doing it. It helps with energy, minimizing energy, but more importantly, think about if the hip swung forward. The hip swung forward, and imagine that the knee did not rotate. What would happen? You try and do it, right? You can't get your foot forward, right? When you lift your foot off, your knee flexes a little bit, right? Some of it is done passively by momentum, but you're also giving your knee a little bit of a help to make sure that your foot clears the ground, right? You're not scuffing the ground as you try and rotate your foot forward. So the hip rotates forward and the knee rotates up a little bit, so make sure that the foot clears the ground. And then the hip swings backward at a slower rate, and the knee locks long before the foot comes into contact with the ground, right? So it's basically preparing to hit the ground. It falls forward, and when it does come into contact with the ground, the knee is locked, and it's able to hold itself, and the robot rocks up and over the planted foot, right? If you were to plot this for human walking, it would probably be more or less indistinguishable from this picture, right? One of the nice things about evolutionary approaches, Mother Nature tends to rediscover the same solution over and over again in some cases. Okay. All right. So now, I mentioned this is one of my favorite papers because this paper just keeps going and going. So they had one evolutionary run that went through phase 1, passive walking, phase 2, hybrid walking, phase 3, fold in the sensors. Phase 4, they continued evolving for another 100 generations, and now they expose the robot to wind, right? Or the guy with the hockey stick, doesn't matter. There's external perturbations that are impinging on the robot as we're evaluating it. And here's a couple quotes from the paper. The robot developed dynamic mechanisms to adapt to the noise, which is a fancy way of saying the robot was able to recover when it was perturbed. So for example, one of the evolved robots, when pushed too far to one side, it was able to recover by stepping a little bit inward, right? Remember, the hip can rotate the leg inward and outward relative to the pelvis, so if it's pushed from one side, it can kind of recover, not unlike how Atlas and Big Dog recover when they're pushed. Okay, how hard can you push these evolved robots before they start to fall over? Well, we can see that in this plot here. So they took one evolved robot, they played it back many, many times, and each time they played it back, they applied more and more external force. And you can see that up to 5, they don't have any units here, so it's hard to know exactly what 5 means here. But up to some level of perturbation, the robot experiences no difference, right? It just adapts and keeps walking at the same speed. After 5 or above 5, the robot starts to stumble, and eventually here it takes 5 steps before it falls over. So it's able to dynamically recover from external perturbation. After phase 4, because it's evolved now in the presence of wind, in the presence of these external perturbations. Okay, keep going. Step 5. Now they continue evolving. Now they introduce mistakes, quote unquote, when building the body. So remember that these morphological parameters are dictating the mechanical construction of the robot. Some of the robots are a little bit shorter or smaller. Some of them have these lead blocks at slightly different positions to change the mass distribution. Imagine that we try and build one of these simulated robots in reality. The mass distribution of the physical robot is probably going to be different from the mass distribution in simulation, right? We're never going to be able to construct a perfect replica of these simulated robots. So we can see how robust they are to manufacturing error, or the difference between simulation and reality, by rebuilding them in simulation and introducing mistakes. So for each of these 22 parameters, when they built the robot, they introduced a certain percentage of error into those 22 numbers when they built the robot. And again, in phase 5 now, that's what they did. Whenever they evaluated one of the robots in the population, they made these manufacturing errors, and then saw how well the robot was able to maintain passive walking and hybrid walking, despite the fact that the robot might be a little taller or a little shorter, or its weight might be a little bit further forward or backward than it was in phase 4. And again, up to about 10% error in manufacturing, which is a pretty high margin. It's able, this evolved robot at the end of phase 5 was able to continue on with passive and hybrid walking despite these manufacturing errors. But as the errors creep up, not surprisingly, the robot can't deal after a while. Okay, very last stage in this experiment here. Now they just took some of the evolved robots and they wanted to see how robust were they to CPG perturbations, right? As we saw at the beginning of our lectures on legged locomotion, you have a particular speed that you're comfortable at walking at. For most of us, it's about 1 hertz, so 1 step per second. But depending on your height, you might take a shorter or longer step. And of course, in certain circumstances, you might want to walk a little bit faster or a little bit slower. How do we do that? Well, we do that in the spinal column by changing the signals to our CPGs, which speed up or slow down this basic oscillation of how we walk. Can our evolved robots do the same thing? So now this plot is again showing you just one robot that we're playing back. This is now, again, hybrid walking because we can see the beats of the CPG pulse. And if you look very carefully here, we can see that the stride length is represented by the purple humps here. And you'll notice that the purple humps are lower around here, which represents the robot taking shorter strides. And the robot takes shorter strides when CPG frequency is increased. So the beat is coming faster, which means the robot needs to take shorter steps in order to keep up with the CPG beat. And indeed it does. So it's hard to see from this picture, but the width between neighboring CPG pulses here actually gets slightly closer together here. The robot takes shorter steps. And then in this period here, they start to decrease CPG frequency. And then they decrease it even further, so it's slower. The CPG frequency is now slower than it was during evolution, and the robot is now taking longer and slower strides. So we can see that the way in which the robot walks is adapting to faster or slower CPG frequencies. So the investigators here are obviously doing it manually. They're telling the robot from outside, speed up or slow down. But of course, we could put this under evolutionary control, and it would be relatively easy for this robot to speed up or slow down based on what's going on around it, right? Yes?
Have we tried to do anything with a larger model? That's really big, sorry. So we evolved in a very complex environment where we were trying to do multiple things all
Yes.
the time, and whether or not we had to run depended on, was there a predator over there? That was never constant, right? So
Right.
have we ever tried to evolve a robot in an environment that had some of that complexity?
Yes, but not anywhere near
Okay.
natural levels, right? So Atlas, which we just saw, is probably now the state of the art in being able to walk under different circumstances and while picking up an object and so on and so forth, right? So again, most work in robotics starts with evolving something that works in a very narrow ecological niche, in this case the declined plane, and then the game becomes how much can you broaden the set of possible environments so that the robot continues to exhibit the desired behavior without failing, right? So to answer your question, the short answer is we haven't gotten very far on that yet, right? I actually mentioned that at the beginning of the course, right? As roboticists, we're able to make specialists, but making generalists that adapt over a wide range of environmental conditions, extremely difficult. But this paper shows one methodology to try and approach that challenge. Okay, while we're on the subject of challenges, this is a perfect segue to the next theme in the course, which is going to be now challenges. We just finished a history of the field. We looked at some of the initial experiments. We looked at the minimal cognition experiment. So can we evolve behaviors that have the building blocks of cognition in there? Then we looked at sort of scaling things up to more complexity, right? We want robots that can exist in our world. They can walk around, they get themselves from point A to point B. They can manipulate objects and categorize and so on. Despite the promise of this field, as I mentioned, it's a very new field. The first experiments only happened 22 years ago. So there's still some open challenges, which from my point of view is one of the things that makes evolutionary robotics so interesting. There are big challenges to which no one has a good answer. So in lectures 13 through 20 here, we're now going to look at some of the open problems in the field and some initial attempts to try and deal with those challenges. We're going to look in a moment in lecture 13 at the issue of modularity. How do we break up things into manageable parts? So divide and conquer, very important. We'll look at issues to do with how do we take the genotype and translate it into the phenotype in the right way that makes it easy for evolution to evolve good robots. We'll look at the neat and hyper-neat algorithms which address other issues in the field. And then we're going to spend 4 lectures looking at one of the most obvious challenges in the field, which is crossing the reality gap. Right? As we've seen now several times, we can evolve robots in simulation to do all sorts of things. If we then take one of those simulated robots and 3D print a physical version of it, it's very unlikely that the physical copy will exhibit the same behavior we saw for the simulated robot. Right? So we're going to look at 4 different approaches that try and help robots cross this reality gap such that if we manufacture them, they do what they do in simulation. Okay. Scalability, we want to try and scale this up. So as we just saw in the passive dynamic Walker example, we had one person who came up with 1 or 2 fitness functions, and they got one kind of robot to do one kind of thing. There's approaches now out there, and our lab is trying to contribute to this, where we incorporate crowdsourcing into robotics. So can we kind of open up these experiments so now we have hundreds or thousands of people that are contributing different fitness functions. They're evolving robots in different directions. They're contributing their own computational effort with their laptops to the problem and so on. How do we scale up these kind of approaches? Because as was just mentioned, we want to try and evolve these robots to deal not just with 1 or 2 variants in the environment, but hundreds or thousands, right? We're going to have to try and scale this up some way. How do we go about doing that? Okay, so let's start with one of the challenges in the field, which is modularity. Why is modularity a challenge? Well, if you look at any branch of engineering, or for those of you that like to code, this comes up in coding all the time. The more and more complex a machine becomes, or the more and more complex your code becomes, the harder and harder it is to make improvements to that machine or that code, unless it's modular, right? When you were learning to code, you probably wrote non-modular code, so you had lots of functions that were calling lots of other functions. You had mixtures of global and local variables. It was hard to see where one part of the code ended and another part of the code begins. For those of you that have taken the software engineering course here, the data structures course, a lot of the effort in those courses is to help you learn how to write modular code, right? Imagine your car where if you changed one of the windows, if you changed out the glass in one of the windows, the entire car no longer worked, right? Doesn't make sense. It's so obvious when you think about physical machines that all the complex physical machines we make are modular, right? You can swap in and out parts and not disrupt the overall functionality of the machine. One of the challenges, one of the problems with evolutionary robotics is if we evolve robots and these neural networks, the robots get better and better at their task, but in most cases they become less and less modular, which is kind of anti-intuitive, right? We're always trying, as we make more complex and capable machines or code, to try and make them more modular. Why does artificial evolution make things less modular? So we want to try and build in ways to help evolution to automatically discover building blocks for the problem we want to solve, and then allow evolution to do that. So in the case of the passive dynamic walker that we just saw, they actually manually put in some modularity there, right? They kind of cheated a little bit. What was the modularity in the passive dynamic walker?
The CPG versus the legs. So you had the leg module,
Exactly.
and the CPG.
You had two modules, right? The neural, and they're identical modules,
Yeah.
one neural network for the left leg, one for the right leg, and then the way in which these modules were energized was dictated by the CPG, right? Which is maybe an obvious way to make things modular, but what about modularizing the upper leg and the lower leg? Might that make sense? Or what about modularizing the pair, the agonist and antagonist muscle group in the leg, right? Where exactly should we divide things, and what's appropriate for the robot at hand?
Do you mean that the robot left on its own tends to evolve spaghetti code?
It tends to evolve spaghetti code left on its own. Now, in all the experiments we've seen so far, we have set all the synapses, right? So we have basically made spaghetti code by connecting all the neurons to other neurons. We haven't got there yet, but later in the course, we're going to see some other evolutionary algorithms that can not just change synaptic weight, but they can add, remove, and modify synaptic weights. And if you do that, evolution creates more and more spaghetti code. It tends to add edges rather than remove them, and makes the neural network less and less modular over time. Anybody have a guess for why evolution does that? If modularity is so useful, why does artificial evolution make things less modular?
Overfitting, maybe, like it can.
Exactly, right? Remember our discussion about neural networks towards the beginning of the course where we talked about overfitting, right? Specialize, make sure you get exactly the right answer under all the different conditions you need. Turns out when you do that with neural networks, a good way to overfit or overspecialize or memorize rather than learn general patterns is to add more and more connections and make spaghetti code. The problem is when evolution does that, it gets itself into an evolutionary cul-de-sac, right, a dead end. Once it does, and now if things change, if the environment changes, you need to swap out one subfunction for another, you can't do it. This is a big problem in evolutionary robotics and neural networks in general.
So did our own brains avoid that by energy constraint?
Did
Our own evolution,
Ah.
we think?
So this is the other flip side, right? This is what deepens the mystery. If you look at biological systems, we are modular at every level of our organization, right? So inside the cell, there are distinct subcellular organizations, and they're modular. You then look at the cell itself, the ultimate module, biological module, right? We're all made up of these modules called cells. Cells are put together into muscles and lungs and hearts and organs and so on. Then you get up to individual humans. We are relatively modular. We exist in certain communities that are separate from other communities and on up the scale, right? Neural organization also seems to be modular. Again, we're not quite sure because it's very difficult to tease apart the interconnectivity in biological brains, but it's looking like brains are modular as well. So why does nature tend to manage to evolve modular systems, but when we apply evolution to our robots, it doesn't work? All right, this is the big issue. What happened in nature that selected for modularity? Once you have it, it's useful, but it's kind of a catch-22. It's hard to think about why it would arise in the first place. There's an immediate advantage to becoming less modular by over-specializing and fitting the current circumstances. Okay, so that's a little bit of a divergence from what we're going to talk about today, but just to try and set the stage, right? We want to try and allow evolution to produce modularity. Okay, so what do we mean by modularity? There's lots of different kinds of modularity. For our purposes today, in lecture 13, I want you to think about tighter coupling within a module and looser coupling between modules. Okay, so again, hopefully as you become better coders and you learn more about software engineering, you get better and better at writing modular code. C++, which introduces object-oriented programming, the whole point of C++ is to make it easier to write modular code. How does that work? Well, when you define a class and you define your methods or the functions that could be executed by that class, you want to have relatively few public methods, right? So if I were to, in the 10 assignments, just give you some code and say, here's some code that allows you to create a shape, draw the shape, and delete the shape, I could say, forget about the internal complexity. All you need to know is that you can call these three functions, and I'm hiding all the internal complexity from you, right? Within the create shape function, there may be a lot of subfunctions that tightly call one another. That's our module, doesn't matter. But create and draw and delete, these three modules are relatively independent of one another. It's pretty clear to you when you call them, you can sort of call them in more or less independent ways, right? Once you have modularity, you can then arrange it hierarchically, right? I could give you the code for creating a robot, right? So create robot, and as you can probably guess, inside that module are a bunch of modules for creating the neural network, creating the body, which is made up of a whole bunch of shapes, and all the way down, right? This is modularity and hierarchy combined. Okay. We've actually already talked about modularity. We talked about structural modularity and functional modularity as it relates to neural networks now. So the code was just there to try and build up your intuition for why modularity is important. We saw structural modularity and functional modularity when we saw the little humanoid robot that grabbed the cube and would shake it up and down and shake it left and right and so on. And so remember that that robot was capable of little motor primitives, right? Little simple actions like up and down 3 times, left and right 3 times. That's what the colored squiggles correspond to. So let's say there are 3 different ones, red, green, and blue, that we want the robot to perform, and we want it to be able to learn those functions and then do them in an arbitrary sequence. Do A, B, then do A twice, then C, then B, and so on, right? Starts to stitch. You want the robot to be able to start to stitch these simple motor primitives together into more complex actions. Take 12 steps to the door, open the door, and exit, right? Those kinds of things. Structural modularity is actually illustrated by the first image from that paper, which is, imagine we have a neural network, and that neural network has 3 separate subnetworks that produce those motor primitives. If we allow this subnetwork to control the robot's motors, it will shake the block back and forth. If we allow this subnetwork to control the motors, the robot does this, and so on. So I've added a little cartoon underneath this figure to help you visualize this. Imagine each of these three modules here is made up of a pair, and there may be the tight coupling by synapses within the neurons for that module. And they may not be completely independent, right? So we can talk about modularity or not, but modularity is really a continuum. How independent are modules? These two modules are completely independent. These, there's one edge connecting them, so they're a little bit coupled. Okay, that's structural modularity. We have different physical structures or different subnetworks that are synaptically independent of one another. Then we looked at functional modularity, which we saw with the humanoid, which is we don't have structural modularity. If we were to look at the structure of this neural network, there are no obvious modules. There's no way to cut this network without passing through a bunch of edges. We saw that there was an advantage to this functional modularity approach, which was you can train the robot to add, basically get this one network to output multiple motor primitives as long as we have some slow neurons that are pushing the fast neurons into the different patterns that correspond to up and down, left and right, and so on. Right? Okay. There's a disadvantage to structural modularity, which we've talked about several times now, which is if we want the robot to learn 1,000 tasks, we might need to have 1,000 separate subnetworks. Not a very good solution. But there is an advantage to this as well, which is if we have separate networks, then we don't have a quadratic increase in the number of synapses. Right? If you think about it, if we have just one neuron, there's one possible edge, which is the edge that connects that neuron to itself. If we have two neurons, how many possible edges are there? There's two in this cartoon, but there's four, right? This one, the self-edge here, and the self-edge here. So one neuron, one synapse, two neurons, four synapses, three neurons, 9, right? And up we go, right? So that's problematic because we don't want to have everything connected to everything else. The brain, the brain has 10 to the 11 neurons and 10 to the 14 synapses. So if you work that out, it's very clear that not every neuron is connected to every other neuron in the brain. If you did, you would have a skull about the size of North America. It would not be pretty. So there are very clear physical constraints on Mother Nature to not connect every neuron to every other one. For our robots, if we're going to instantiate these neural networks in a circuit, it doesn't really matter how many connections we have. But it does matter from an evolutionary point of view, because the more connections we have, what happens from an evolutionary point of view? We're evolving neural networks that have more and more neurons. If we assume that every neuron is connected to every other synapse, what happens to the genome that we're evolving?
It's ridiculously huge.
It's ridiculously huge, right? And evolution's just going to throw up its hands and say, this space is just way too large. I can't find a good solution in this massive space. So in some of the experiments we see as we go forward, we're going to see this structural modularity, which has the disadvantage that we have separate subnetworks, but at least it makes things easier on evolution. We don't have this exponential increase in the number of edges. Okay, so in today's lecture, we're going to look at an experiment which actually focuses on this issue of structural modularity, not functional modularity. Okay, so if we're going to do structural modularity and we want a robot like Atlas to do bipedal locomotion and pick up blocks, let's make two networks, one for walking and one for picking up blocks. Seems obvious, right? But is that really the best way to create modules for that robot and for that pair of tasks? It seems obvious to us, but remember at the beginning of the course I said thinking about thinking is misleading, right? When you watch the Atlas video, it seems obvious that there are two separate functions, locomotion and object manipulation. From the point of view of the robot, it may not seem that way. How is that possible? Well, here's a little toy example to show you how this might be. Imagine we have one of our little wheeled robots here, and it's got its 5 proximity sensors out here, And we can clearly see from our point of view, from a distal perspective, looking from outside the robot, that there's two separate situations going on here. The robot is driving past the cylinder, or it's driving past the block, right? Or the robot is locomoting, and now it's manipulating an object. Or now it's locomoting while manipulating an object. We're looking at the robot from a distance and saying, clearly there's two separate things going on here, right? Now, let's adopt a proximal perspective on behavior, which is, let's try and see the world through the robot's eyes, more or less literally here, right? So if we take the 5 proximity sensors and we actually plot them, what is the robot seeing in these two conditions? Exactly the same thing. From the robot's point of view, these are not two separate situations. They're exactly the same. Now, this is a cartoon example, so the moment the robot moves, yes, they're probably going to look different, right? The robot can exploit its motion to see that there is two different situations here. But this is just meant to illustrate that we have to be very careful. If we say we want the robot to perform X, Y, and Z, that's fine. The robot may actually evolve the ability to exhibit X, Y, and Z, but from the robot's point of view, there may be no X, Y, and Z. It might be a continuum, or it may be A and B. It may come up with 2 different distinctions rather than 3, and they're very different from our distinction. Okay, so what this means is we want to allow the robots to become modular, but we don't want to build in our biases. We don't want to tell the robot what modules are appropriate, what sub-functions are appropriate for the task. We would like evolution to create modularity and do it in the right way. Create the right sub-functions that are appropriate for the robot and the task, not what we think is appropriate, because we could be wrong. Thinking about thinking is misleading. Okay, so today's reading comes from, again, a very early paper in the field where they tried to tackle this issue. They used the Kepler robot that you see here. Remember that this robot itself is modular. You can attach different components on top. In this case, they gave the robot this little gripper here, and the task is for the robot to move around inside a little enclosure, and there's a bunch of these little wooden pegs or cylinders. The robot has to find these pegs, grasp them with its arm. So here you can see the arm holding a little sugar cube. Grasp the object, lift it up, drive to the edge of the arena, and throw the object out of the arena. Right? We want to eventually have robots that clean up around us. Here's a good start. Okay. Not that different from what we've seen before. This robot has 6 infrared sensors, which are these 6 gives it proximity information in front of it. It has a 7th sensor, which is a light barrier sensor. So there's a little light beam that shone from the left finger to the right finger, and if an object comes inside its gripper, that light barrier is broken, and that information is passed into the robot's neural network. So it can sense kind of what's in front of it and whether there is something inside its gripper or not. There's 4 motor neurons, and these motor neurons can turn the robot to the left, they can turn the robot to the right, they can trigger this behavior, which is object pickup, or they can trigger this behavior, which is object drop. So there's 4 different things the robot can do at any point in time. Okay, so let's think about this for a moment before we evolve the robot, right? And let's commit the sin of thinking about thinking here, taking the distal perspective. Well, it's obvious what the functionality is here, right? The robot, let's define 1, 2, 3, 4, 5, 6 subfunctions. The first one is explore the environment and avoid walls, right? You're never going to find a cylinder unless you move around, and probably moving around randomly makes sense. A1 and A2 here is basically just sketching out a Bradenburg vehicle, right? If there's proximity on the left, turn to the right. If there's proximity on the right, turn to the left, and you'll avoid obstacles. Keep doing that until your light barrier is broken. Then do something else. That's module 1. Recognize that there's an object there. Make sure it's positioned. Module 3, pick it up. Module 4, move towards the wall while avoiding the other objects or obstacles. Module 5 or subfunction 5, recognize the wall, move right up close to it so your arm or your gripper is rotated out and over it, release the object. Obvious, right? There should be 6 modules here. Okay. Let's see what happens. So in order to test these ideas, in this case, they evolved 5 different kinds of neural networks on this simple robot. In all 5 of these cases, the fitness function is the same. Find the objects, drop them outside the arena. These different networks increase in complexity. So network A, we have our 7 sensors down here and our 4 motors, which correspond to turn left, turn right, pick up, or drop. Network B contains, is feed forward. So we have stuff going from the sensor to the motor layer, and we've introduced hidden neurons. So what do hidden neurons do? What advantage does B have over A? They don't allow for memory. That's recurrent connections, which as you can see is coming in network C. What do the hidden neurons do? We actually talked about this when we talked about Marvin Minsky passing away at the beginning of the course.
They allow for other functions.
They allow for other functions than this. This only allows for linear transformations of sensation into action. The moment you introduce hidden neurons, it also allows evolution to play with nonlinear transformations from sensation into motors, which may or may not be useful here. One of Minsky's biggest contributions to the field of AI was proving that there's certain things that this network can't do relative to this one. Okay, and then network C, as we've seen before, now we add in recurrent connections. It's drawn here in a way that's slightly different from what you've seen before. You can see that there are a bunch of synapses that connect the 7 sensors to the 4 motors. So there's direct connections from sensors to motors. But there are also connections from the 7 sensors to the 2 hidden neurons. Those 2 hidden neurons are attached to each other and then passed on to the motors. So we have recurrent connections going on here. It's just drawn in a slightly different way here. Network D is the researchers now manually building in some modularity. And this is structural modularity, right? We can see here's one subnetwork here, and here's the second subnetwork here. And we can see that there's 2 motor layers here. So what does that mean? That means that under certain circumstances, so all of these 8 neurons are going to light up for every time step of the simulation. But depending on the circumstances, these motor neurons are going to be allowed to control the robot and not these. Under other circumstances, these motor neurons are going to control the robot and not these. So basically we have sort of 2 candidate actions, right? The robot is kind of thinking, I could do A or B, and then there's something that happens in the environment that it goes with B or it goes with A, and that's being built in by the researchers. So the first module is used to control the robot when the gripper is empty, when it doesn't have a cylinder. The moment the robot grabs a cylinder and lifts it up, not even when it lifts it up, just when the light barrier is broken. The moment the light barrier is broken, these motors no longer control behavior, these ones do. Now, what exactly the robot does when its gripper is empty or full is, again, up to evolution. Evolution is evolving these synaptic weights. So the researchers say there's 2 modules, and this is when these are the conditions under which one module is in control or the other. But evolution, you figure out what to do in these 2 conditions. So in the previous slide, I said, well, we could break this up into 6. We can also break it up into 2, right? This is kind of intuitive. The robot should do different things when its gripper is empty or full. Okay, that's networks A, B, C, and D. Here's network E, the 5th and final one. And as you can imagine from our discussion now, network E, this is an attempt for the researchers to say, evolution, you're going to be able to make things modular if you want. You don't have to. And if you do make things modular, you can make them modular in whatever way you want. You don't have to break it into the two modules that we forced you to use in Network D. Okay, how does this one work? This one takes a little bit to build up an intuition for. We have our 7 sensors down here. We have our output neurons here, and you can see that there's 4 groupings, which correspond to the 4 basic behaviors. Right? For each one of the 4 basic behaviors, there are 2 motor neurons for each group, and also these 2 things called selector neurons. And the selector neurons are going to select or dictate which of these 2 motor neurons is used for triggering the left motor, right motor, pickup or release. Okay. You'll notice that there are synapses that are going from every sensor to every motor neuron and also to every selector neuron. Okay. So how do the selector neurons work? At every time step, we look at each pair of selector neurons. If the left selector neuron has a larger value than the right selector neuron, that's the neural network saying, I want this neuron to control this particular motor output. This motor neuron might be 0, which means don't turn left. Right? Or this neuron might be 1, which means turn left as fast as you can. Right? Again, this output is just controlling how much of that behavior is done. You might have 0 for the left motor neuron and 1 for the right motor neuron. So the robot is saying, well, I could spin my left wheel not at all or as fast as I can. The selector neurons are then going to gate that and decide which one actually gets sent to the left motor. Make sense? Okay. So if you look carefully, you can actually see 1, 2, 3, 4, 5, 6, 7, 8 groupings here. So if we define states, discrete states of this network based on which which selector neurons control the motor neurons. So state 1 would be left selector is greater than right selector neuron. State 2 is the opposite. How many possible states can this network exist in? So as the robot is moving around, the sensor values here are changing, which means the values of the selector neurons are changing, and at a point in time, the left value may be higher than the right value, but then suddenly the right may become higher. The right selector neuron may take a value higher than the left selector neuron, and now suddenly this neuron is controlling the left motor. So there are discrete switches that can occur inside this network, and we're going to treat these discrete switches as discrete states. How many different states are possible here? 16, right? So if you think of these here as 4 groups, they can be in one of 2 states, right? Left is larger or left is less than the right. So we have 2 to the 4, which is 16 possible discrete states. So if evolution wants, it can evolve 16 separate modules, and it can decide what exactly the robot does when any one of those modules is in effect. Okay, so now, as you can imagine, they're going to evolve the robot with these 5 different networks, and it's going to allow, depending on how well or how poorly the robot does with any of these 5 networks, we can understand for this task how important internal neurons are, which again allows us to create nonlinear functions. One important nonlinear function for a robot or any animal is to be able to react very differently to seemingly very similar sensory input. You can think of some examples of that, right? That's one kind of nonlinear function that might be useful. Recurrent connections give you memory, so obviously remembering what happened in the past is important. It's also important where you may be faced in the present with exactly the same stimuli, but what you should do in that circumstance is dictated by what just happened, right? the adaptive advantage of memory. Okay. Modularity is important for the reason we said. We want to have different modules and have the robot be able to switch between different situations, and by doing so we can get away with many fewer connections. Okay, so here's our fitness curves as we've seen before, and as you can see from the topmost picture here, network E is the clear winner. B tends to catch up after a while, but it takes a while. So E is definitely better. How did they actually evolve these networks? Well, they took, again, a population of these controllers, and it might be a population of network A or a population of network B, and so on. They took each controller out of the population, dropped it into the robot, and they evaluated the robot with that controller 15 times, which they called epochs. And at each of these 15 evaluations, they took the robot and put it in a different position in the arena and said go. For each one of these 15 placements, they allowed the robot to perform 200 actions or 200 ticks of its internal clock, or they would stop the epoch early if the robot managed to grab an object, take it to the edge of the arena, and drop it outside. They'd stop the epoch early, start the next one of the 15, and so on. They did that for 1,000 generations, and they did that evolutionary run. They did 10 of them for each of the 5 networks, giving us a total of 50 evolutionary trials that were done in this case. They did it in simulation. They did all the evolution simulation. Then they took these evolved controllers and dropped it into the physical Kepra. I just told you about the simulation to reality gap, right? So with the simple robot, they were very careful to make sure the physical robot did more or less what the simulated robot did, which is easy when you got a little simple wheeled robot, not easy when you have something like Atlas. So here the reality gap isn't too bad. Okay, so then they had, remember they did 10 runs for each of the 5 networks, so they had a total of 50 controllers they wanted to try out, which was the best controller in the population at the end of that evolutionary run. They've got 10 good controllers from set A, B, C, and D. They put them on the physical robot and then looked to see how successful were those robots, and success was drop all the 5 obstacles outside of the arena. Okay, so E is clearly doing better. So the fact that E did better than D tells us something immediately, which is the manually derived modularity that was built into D. Go back to D for a moment, right? Forcing evolution to use 2 different modules, one for when the gripper is empty and one is full, is not a good way to create modularity. The fact that E, a modular network, did better than A, B, and C tells you that modularity is useful. But evolution has an idea of what kind of modularity is appropriate here, and it's different from what we thought. Yeah? Okay. So it definitely came up with a different solution to what we thought, and I'll show you a picture probably next time of what that actually looks like. Remember that there's 16 possible states that are possible here. Evolution didn't use the 16 states, it actually only used 2. So in one of the most successful evolved controller here, the left motor pickup and release, within those 3 behaviors, one of the 2 selector neurons was always higher than the other one. So there wasn't switching back and forth between the pair of neurons. It was only in the right motor grouping that evolution would periodically switch selector neurons, which would switch the output neurons. So those are the 2 modules. And I think we're out of time, so we'll actually look at what these modules are and how it enabled the robot to succeed next time. You have a quiz due tonight, and you've got assignments 7 and 8 to work on, which is due Monday night. Good luck. Thanks.